Okay, so we're over here now. I should be just about finishing up 3.5, and maybe I can sneak in a little bit of 3.6. Okay, so if I just go up to 3.6 for the week, I'm good. So I'm slightly ahead right now, but I might fall behind, I might get sick, or my computer might go down again. So it'd be nice to be a little bit ahead. Okay, that being the case, there's a good chance I'll finish a little bit early today. I'll finish up some problems in 3.5, sneak in a little 3.6, and then let you ask questions. Okay, and if there aren't any questions, we can just stop, or maybe I'll just keep going to 3.6. Okay, quiz this week. What is it going to be on? Well, it's almost certainly going to be on more derivatives. All right, so chances are you'll be all kinds of derivatives that we've had up to now: products, quotients, trig, some implicit differentiation, but we'll see how it goes. Okay. All right, so let me go back and do some more problems from here and maybe sneak in a little bit of 3.6. Okay, so back to implicit differentiation. And one thing we're going to do now is actually find the slope, but we'll have to plug in x and y. So notice when we differentiate implicitly, our derivative has x and y. So now if they say you're at the point 2, 1, before we were only plugging in the x. Now you might have to plug in the x and the y, right? And by the way, you may notice, say, what's the equation of this look like? I don't know. I mean, me, myself, right now, I have no idea what this looks like. It may not even be a function, right? So it might have some weird graph. I'm not tracing it obviously because I'm just making up stuff. It may not even be a function, but whatever it looks like, I still want to be able to talk about the tangent to the curve, right? So sometimes for a graph, you can see I actually have the equation of the tangent line. Sometimes you're going to get a hold of the tangent to the curve better than you can get the curve itself, right? So if you ask me right now, what does this look like? I don't know. Okay. Can I solve for y? Not very easily, but we don't care. All right. So for implicit differentiation, you have x and y's mixed together. For explicit differentiation, it was y as a function of x, or p as a function of q, or s is a function of t, or whatever, right? But now x and y's are all mixed up. Okay, so I take the derivative of the left side and the derivative of the right side. Let me get the right-hand side easy. What's the derivative of 1? 0. Okay, now I differentiate this. Okay, so for implicit differentiation, if you see an x, just do the usual derivative. If there's a y, though, you have to remember to tack on an extra dy dx, because y is implicitly a function of x. Okay, so the derivative of x squared, 2x. The derivative of, okay, originally that's a negative xy. I'm going to pretend it's plus a negative xy. Okay, I think it's easier if we tackle it that way. So instead of minus xy as in the original, it's plus a negative xy. So the first function is negative x, the second function is y. Okay. All right, so it's a product. So we do the product rule. First function, negative x, times the derivative of the second. So the derivative of y is 1 dy dx. Plus second function y times the derivative of the first. The derivative of negative x is negative 1. And since I was differentiating with respect to x, I don't need to put anything extra there. Okay, the derivative of negative y squared, negative 2y, and since there was a y involved, times dy dx equals 0. All right, then let's see what happened after that. Supposed to clean that up. Okay, oh, I know what I did. Okay, I can solve for dy dx. But in this case, since they tell me 2, 1, I can just plug in 2 and 1 automatically. You're allowed to do that. Just makes the calculation a little bit nicer. Okay, so I put a 2 here, a 2 here, a 1 here, and a 1 here. That's what I did. Okay, because we're plugging in 2 and 1. Okay, so I have 4 minus 2 dy dx minus 1 minus 2 dy dx equals 0. Okay, so 4 minus 1 is 3. And negative 2 and a negative 2, so minus 4 dy dx. Okay, do the algebra, so dy dx is equal to 3/4. Right, then point slope form. We know the way the game works. Okay, the equation of the tangent line, y minus y1, so y minus 1 equals m 3/4 times x minus x1, x minus 2. So this is the equation of the tangent line. Stop. You can stop right there. All right, then 33. Find the equation of the tangent to the curve y squared equals 5x to the 4th minus x squared at the point 1, 2. In the book, they actually give you the name of this. You don't have to worry about that. Don't memorize it. I don't have it memorized. I think it's something called it. Maybe I shouldn't waste time finding it. Yeah. Campile of Eudoxus or something like that. Never mind about that. Maybe just cover it up. Don't even look at it. So find the equation of the tangent at the point 1, 2. Okay. So here we go. 2y dy dx, because there's a y, needs a dy dx. But notice the right-hand side only consists of x's, so I don't have to put any extra d stuff. So the regular 20x cubed minus 2x. Okay, solve for dy dx. Just divide both sides by 2y. So 20x cubed minus 2x divided by 2y. Now I plug in 1 for x, 2 for y. So put a 1 there, a 1 there, and a 2 there. So the bottom is 2 times 2, which is 4. This is 20 minus 2, which is 18. So 18 over 4, which reduces to 9 over 2. And we're home free. Point, slope. So y minus y1 equals m times x minus x1, x minus 1, stop. This is the equation of the tangent line. Okay, so I got the equation of the tangent line, even though I don't know what this graph looks like. I don't know, and I don't care, frankly. We don't need to know. Okay. The tangent line, though, is right here. All right, so there we go. Okay, next part of this same section is the inverse trig function. Derivatives of inverse trig functions. Page 213. Okay, we're only going to do inverse sine, cosine, and tangent. The inverse secant, cosecant, and cotangent, those derivatives actually exist. They're not really used that much, so we're not going to go over that. I'm not going to hold you responsible for it. Okay, I will show you quickly the derivation of each of these, though. Okay, so I'll show you. The book goes over it also. I'll show you my version of it. You're not responsible for the derivation. I'm responsible for the derivation. So I'm just going to fly through it quickly. If you are interested in it, go ahead and look at it. If you don't really care, then don't worry about it. But I am going to fly through it. Okay, so y equals inverse sine of x. Find dy dx. Okay, so the trick we're going to do is get rid of the inverse, write it as sine of y equals x. And I'm going to write it as x over 1. Okay, so this means the same thing as this. If y is inverse sine of x, sine of y equals x. Now I differentiate implicitly. Implicit differentiation. Cosine y, and since there's a y, dy dx equals 1. So dy dx is 1 over cosine y. Okay. Then I have to do a little bit of trig. Okay, so I draw myself a triangle. Y is the angle. So I put y here. Okay. You might recall from trig that sine is the opposite over the hypotenuse, right? Sine is opposite of hypotenuse. So x over 1. Do some Pythagorean theorem, and this comes out to be radical 1 minus x squared. You can convince yourself of that, but that's what it comes out to be. So 1 divided by the cosine of y. Cosine is adjacent over hypotenuse. So it's radical 1 minus x squared divided by 1. Well, if you divide by 1, it's just radical 1 minus x squared. Okay, so there it is. Okay, so I've shown that the derivative of inverse sine is 1 over radical 1 minus x squared. Okay, you can put that in your next cheat sheet. You might say, I don't follow anything you did over here. That's okay. Some of you might get it. It's provable. Okay, but at least I showed it to you as opposed to here it is, just use it. Some of you might say, where did it come from? So this is where it came from. Okay, you change inverse sine to sine, and then you differentiate implicitly, do a little bit of trigonometry, and that's what it comes out to be. Okay, something similar happens for inverse cosine. Okay, so let me run through that very rapidly. So y equals inverse cosine of x means the same thing as cosine y equals x. I sneak in an x over 1 when I'm ready to draw my triangle. Okay, so I differentiate implicitly. Negative sine y times dy dx is equal to derivative of x, which is 1. Divide both sides by negative sine y. So dy dx is negative 1 over sine y. Okay, so again, I draw myself a triangle. The angle is y. Okay, cosine is adjacent over hypotenuse. So I put x for the adjacent, 1 for the hypotenuse. And that makes this side square root of 1 minus x squared. The triangle is almost the same as this. Okay, do some a squared plus b squared equals c squared. This is radical 1 minus x squared. Okay, so dy dx is negative 1 over the sine of y. Sine is opposite over hypotenuse. So it's radical 1 minus x squared divided by 1. And again, if you divide by 1, just forget about it. So negative 1 over radical 1 minus x squared. Okay, bottom line, the derivative of inverse cosine of x is negative 1 over radical 1 minus x squared. Okay, so again, you're not responsible for the derivation. I'm responsible for the derivation. You can put this in your next cheat sheet. Okay, and one thing you may notice, here's the derivative of inverse sine. The derivative of inverse cosine is exactly the same thing, except there's a minus. Okay. And then inverse tangent, derivation. Same thing, I'll just fly through it. Y equals inverse tangent of x means tangent of y is x, or x over 1. Differentiate implicitly. Derivative of tangent is secant squared. So secant squared y dy dx equals the derivative of x, which is 1. Divide both sides by secant squared of y. So dy dx is 1 over secant squared y. But the reciprocal of secant squared is cosine squared. So cosine squared y. All right, then I draw my triangle again. Y is the angle, tangent of y. Okay, tangent is opposite over adjacent. So opposite side I put x, adjacent side I put 1. Do your Pythagorean theorem, your a squared plus b squared equals c squared. You can get the hypotenuse to be radical 1 plus x squared. Okay, so dy dx is cosine squared of y. So the cosine is adjacent over hypotenuse. So 1 over square root of 1 plus x squared, squared. Okay, because it's cosine squared. 1 squared is 1. A radical squared, you just take off the radical. So 1 over 1 plus x squared. Okay, so bottom line, inverse tangent's derivative is 1 over 1 plus x squared. Okay, so yes, I ran through the derivations quickly. You might say I didn't follow that derivation. That's okay. And I know I went through it 100 miles an hour because I know you're not responsible for it anyway. I'm responsible for it. But maybe some of you wanted to know, where did you come up with that? Somebody just picked it out of a hat or whatever. Just know, okay, these derivatives can be derived. You can show it analytically using calculus, inverse trig functions, and a little bit of right triangle trigonometry. Okay, so inverse sine, inverse cosine, and inverse tangent. And I'll also show it to you in the text. The text does this exact same derivation. Inverse trig functions. Okay, so bottom of 214. here's what you want to know. Okay, so the derivative with respect to x, dtx, inverse sine, 1 over radical 1 minus x squared. Inverse cosine, same thing, except it's a minus. d dx of inverse tangent of x, 1 over 1 plus x squared. As you can see, the derivatives of inverse cosecant, inverse secant, and inverse cotangent, they exist. Okay, we're never going to use it in our class, but you can derive these, do the same kind of trick as I did, draw your triangle and all that stuff. So here they are for your curiosity, but we're never going to use them. We're only going to use these three. So as far as we're concerned, just kind of cover these up and just look at these. And once again, if we were meeting face to face, I'd make you guys memorize it. But since we're not, you guys can put it on the cheat sheet. There's one thing nice about all of them, that if you were meeting with me face to face and say memorize it, here's one thing I would say. Okay, what do they all have on top? 1. What do they all have on bottom? A 1 and an x squared. So that helps if you were to memorize it. Yeah, I'm saying memorize. Maybe you're, hey, I'm not forced to memorize it in this class. Maybe your Calc 2 teacher is going to make you memorize it. So who knows, right? Okay, so they all have a 1 on top. They all have 1 and an x squared in the bottom. Okay, for inverse sine and cosine, they have the square root and a minus. And inverse cosine is exactly the same, except there's a negative in front of it. Okay, and then inverse tangent, no square root, and it's a plus. Okay, so that's what it would tell you guys if we were meeting face to face in terms of how do you memorize this crazy thing, right? They all have a 1 on top. The bottom, they all have a 1. They all have an x squared. Inverse sine and inverse cosine, square root, minus. Inverse tangent, no square root, and there's a plus. Inverse cosine, there's a negative. All right, so now do some problems involving these derivatives, and then that's pretty much about it. Okay, so number 50. In case you're wondering about this strange assignment, I had to tiptoe around the ones that had inverse sine, cosine, and tangent. So why such a strange, assortment there? Just show you. Okay. I wanted to avoid inverse secant, inverse cotangent, right? So out of all of these, with the inverse trig functions, I wanted to make sure I was only doing inverse tangent, inverse sine, and inverse cosine. And again, arc means the same thing. So if you see arc cosine, that's the same as inverse cosine. Arc tangent, inverse tangent, right? So that's the reason why the assignment looks so funny. Is I wanted to make sure that I only did inverse sine, cosine, tangent. Okay, so anyway. So y equals inverse tangent of x squared. So you go 1 over 1 plus this thing squared. So 1 over 1 plus x squared squared. And then by the chain rule times the derivative of x squared, which is 2x. Okay, then just slide the 2x on top. That becomes 1 plus x to the 4th. All right, 52. G of x is arc cosine of square root of x. That's the same thing as inverse cosine of radical x. This is short to the right, but this is easier to type on a computer, right? It's a little bit hard to get that on your computer without special characters and stuff, but it's pretty easy to type on your computer, ARCCOS. Anyway, okay, so how does arc cosine work? Arc cosine will do this. All right, so negative 1 over square root of 1 minus this thing squared, our formula. So it's 1 over radical 1 minus root x squared. That's nice, because square root of x squared is just x. But then by the chain rule, it's times the derivative of radical x, okay, which is x to the 1/2. So what's the derivative of x to the 1/2? 1/2 x to the minus 1/2. Then a little bit of cleanup. Negative 1 over, okay, the 2 on the bottom. X at a negative half means square root of x on the bottom. And this is radical 1 minus x. Okay, so the 2 is here. X at a negative half is there. This becomes square root of 1 minus x. And then the last thing is you can join these two, and you should, right? If you have a square root of x, square root of 1 minus x, you're allowed to just multiply them. So negative 1 over 2 radical x minus x squared, best final answer. Okay, and then 57, and then that's the last thing I'll show you here. Okay, y equals x inverse sine of x plus radical 1 minus x squared. Okay, so I want to show you at least one of each. Okay, so I've already shown you one involving inverse tangent. I showed you one involving inverse cosine, arc cosine, and I want to show you one with inverse sine. That was as much as I'm going to show you. Okay, so find the derivative of this. So this looks like it's going to be a product rule, right? First function is x, second function is inverse sine of x. This is a chain rule. It's 1 minus x squared raised to the half power, right? All right, so y prime first times the derivative of second. So derivative of inverse sine, we now know is 1 over radical 1 minus x squared. From over here. Okay, so first times the derivative of the second, 1 over radical 1 minus x squared, plus the second, inverse sine of x, times the derivative of the first, but the derivative of x is just 1, so you don't even have to write it. All right, plus the derivative of this. Remember, that's like 1 minus x squared to the half. So half comes down, 1 minus x squared to the negative a half. Then by the chain root times the derivative of the inside, which is negative 2x. And then let's see, I cancel that 2 with that 2. So I have negative x on top and radical 1 minus x squared on the bottom. Okay, so just try to put it all together. I have, let's see, made a mistake here, sorry. This should be x. So all of that should actually be gone. Okay, this is x over radical 1 minus x squared. This is also minus x over radical 1 minus x squared. So they cancel out, plus inverse sine of x. So all I have left is just inverse sine of x, which is weird. Okay, this is all gone, I messed up here. So the final answer is just inverse sine of x. So the derivative of this big mess here, strangely enough, just comes out to be inverse sine of x. Okay. All right, I'm done with what I was going to do, except introduce a little bit of 3.6. Okay, so I'm done with 3.5. So schedule-wise, I'm up to here, so I'm a little bit ahead. I'll sneak in some of 3.6 and then I'll stop. Okay, so I'll be done in 3 or 4 minutes or something like that. So if you have questions you want to ask, be ready to bring them up. Otherwise, I'm done. Okay, so think of questions you might want to ask, and I'll be done shortly. Okay, so 3.6, we're now going to take the derivative of log functions. How do I take the derivative of log functions? Okay, so let me just introduce the idea here. 3.6. So what is the derivative of natural log of x? ln x prime. Okay, and to motivate that, I know that the inverse of the log function is the exponential function. So I'm going to start off by saying y equals ln x. Since I already know how to differentiate the exponential, I'm going to exponentiate both sides. That means put an e like this, e to the y, e to the ln x. Okay. What does that make the right-hand side? x. So I have e to the y equals x. And just like a trick I did a moment ago, I will now differentiate implicitly because I know how to differentiate e to the y. Okay, so implicit differentiation. What's the derivative of e to the y? E to the y times dy dx. Okay, and the derivative of the right side is 1. Okay, then I just divide both sides by e to the y. So dy dx is 1 over e to the y. But e to the y is x. So dy dx is 1 over x. Okay, so the new derivative rule. Okay, the derivative of the natural log function is 1 over x. And again, you're supposed to memorize it. It's really not that hard to memorize, but since I said already at the beginning of the semester, you can have a cheat sheet, go ahead and put in your cheat sheet. This should not be that hard to memorize. And again, maybe your Calc 2 teacher is going to make you guys memorize it. So the derivative of the natural log of x is 1 over x. Again, if you say, I don't understand this derivation, that's okay. You're not responsible for that. I'm responsible for it. Okay? You're responsible to know that when you have the natural log function, the derivative is 1 over x. And of course, the associated chain rule still applies to that. Okay. Now, what if you have a log to any other base? As you might guess, when I had e to the x, the derivative was e to the x. And if I have any other base like a to the x, it was more complicated. It was a to the x ln a. Likewise, if I have a log to some other base, it's a little bit tougher, but we're going to change it so that there's an ln. So what's the derivative of y equals log base b of x? Well, one of the properties of logs by the change of base rule, right? Log base b of x, I can write as ln x over ln b. Remember any rule like that? Okay, so log base b of x, you can write it as ln x over ln b. And the reason why I'm circling that and sticking a 1 is because think of this as 1 over ln b is a coefficient. Okay, 1 over natural log of b is a coefficient of ln x. So therefore, y prime is the coefficient 1 over ln b times the derivative of ln x, which we now know is 1 over x. And we clean it up as 1 over x ln b. Okay, so bottom line result, you can see it's a little bit harder. Put it on your cheat sheet if you wish. So what's the derivative of ln x? 1 over x. What if you have a log to any other base? The log base b of x prime is 1 over x ln b. Again, clearly not as nice. So how about base 10 log, right? You like base 10 back in algebra, perhaps. What's the derivative of log base 10 of x? 1 over x ln 10. How about log base 2 of x? What's the derivative? 1 over x ln 2. Clearly, it's not as nice. So our favorites are base e. So like we said, the derivative of e to the x is e to the x. If you have some other base like b to the x, the derivative was b to the x ln b. Okay, so likewise, for a natural log, derivative is easy, 1 over x. If you have a log to some other base, log base b of x, the derivative is 1 over x ln b, like this. Okay, so page 218. The derivative with respect to x of log base b of x is 1 over x ln b. Clearly not as nice. And the log will obey the chain rule also. Okay, so chain rule for logs, page 219. The derivative of ln u is 1 over u times du dx. So there's a chain rule involved also. This pretty much says the same thing. So if you have the derivative of ln of g of x, you would go 1 over g of x. There it is. And then by the chain rule, times g prime of x. And I'll show you some examples of that later. Actually, they give you one example here, but I was going to show you a derivation of the power rule now, and then I'll stop. Okay, so at least look at this one example, and I'll do some problems tomorrow. Find the derivative of natural log sine x. So derivative of ln is 1 over. So first you go 1 over sine x, and then times the derivative of sine x, which we now know is cosine x. So you have cosine x over sine x, which turns out to be cotangent x. Okay, so the derivative of natural log sine x is cotangent x. Okay. The last thing I'll show you, and this is another one of those where you're not responsible for, I'm responsible for, is actually now to prove the power root, which I first introduced way back in section 1 or something, right? We said, oh yeah, the derivative is n x to the n minus 1. I never proved it. Okay. Now this is a proof. Okay, so, and n can be any real number. So y equals x to the n. Take the natural log of both sides. ln y equals ln x to the n. And there's a property of logs that says I can bring the n in front. Right? So ln y equals n ln x. Differentiate implicitly. We now know derivative of ln y is 1 over y dy dx equals n times the derivative of ln y is 1 over x. Multiply both sides by y. Clean this up. That cancels out. So dy dx is n times y over x. What was y? Y was x to the n. I have x to the n divided by x, which is x to the 1. And x to the n divided by x to the 1 is x to the n minus 1. So there it is. Dy dx is n x to the n minus 1. So finally, we're able to prove something I've been saying way back in section 1 and 2. This is the power root. I never proved it. Now I've proved the derivative of x to the n is n x to the n minus 1, as you can see here. Okay. All right. So as I said, that's pretty much about it. So let me stop here and stop the share for a moment and check what we have in terms of the chat. Okay. So what time is it? Maybe 15 more minutes. Okay. So I see 3.5, 15. 3.4, 17, and 41. 3.5, 31. 3.4, 47, 61. Okay. For those of you that need it, Prasanna is doing a problem in the chat. The one that said e to the x over y times y plus x times dy dx equals 1 minus dy dx. So that helps. You can do that. Okay, so let me check 3.5, 15, 3.4, 17, 41, 31. Okay, I'm not sure I'll get to all of these, but we still have tomorrow. Okay, so tomorrow again, come with any of these questions. All right, so I'm going to leave the chat and go back to sharing the screen again. That's the only way I can do this. Yeah, so usually once I switch to sharing the screen, I won't be able to see the chat anymore. So go back and forth. Okay, so what do I want to do? How about 3.4, 17? Okay. 3.4, 17. F of x is equal to 2x minus 3 to the 4th. Times x squared plus x plus 1 to the 5th. Okay, so this is a product root and a chain root. First function, second function. So f prime is first function times the derivative of the second. So the derivative of the second involves a chain root. So 5 times x squared plus x plus 1 raised to the 4th power. And then by the chain root, it's times the derivative of the inside, which is 2x plus 1. Okay, so all of that was first times the derivative of the second, plus, and I think I'll scroll down, otherwise I'm going way out here. So plus second function, x squared plus x plus 1 to the 5th, times the derivative of the first. So derivative of the first function is 4, 2x minus 3 cubed. And then by the chain root times the derivative of the inside, which is 2. And I'm going to stop right there. What will you have to clean up on the test? Maybe just 4 times 2 equals 8 and leave all the rest alone. Normally you put the 5 in front. Okay. You could actually do a lot more algebra if we don't feel like it. Okay. I'm testing you mostly on calculus, not on algebra. So I'm going to stop there to go to the next one. Okay. 41 was asked for, I think. 41. Okay, if I don't put the section number, it's implied that it's the same section. So 41. Sine squared e to the sine squared t. Okay, so f of t is sine squared of e raised to the sine squared of t. Oh boy. So this has a lot of stuff here. The outermost function is the scoring function. Okay. You're taking sine squared of something. So the outside function is squaring. So it's sine of something squared. Okay. So 2 sine of e to the sine squared t. Okay, so that takes care of the raising to the second power. 2 sine of that. Then times by the chain root the derivative of sine, which is cosine. E to the sine squared t. And now it's times the derivative of the inside function. Okay, so outermost is 2 squaring, then sine, derivative of sine is cosine, times the derivative of the inside. So the derivative of e to the sine squared t is e to the sine squared t. And then by the chain root times the derivative of sine squared t, which is 2 sine t to the first power, right? Pretend it's sine of t squared. That's ultimately what it means. Right? Same thing over here. Sine squared of all that, it's that whole thing squared. So 2 sine t, and then by the chain root times the derivative of sine t, which is cosine t. Okay. So that's that. 47, cosine of sine of 3 theta. So that might get a little tricky. So first derivative of cosine is negative sine. Okay. Copy that. Then by the chain root, it's times the derivative of the inside. So what's the derivative of sine 3 theta? Cosine 3 theta times the derivative of 3 theta, which is 3. And this one I definitely want to clean up before I take the second derivative. So I'll put the 3 in front. So negative 3 sine of sine 3 theta times cosine 3 theta. Okay, so that's y prime. And I'm going to think of this as the first function. This is the second function. Sort of like f and g. So for y double prime, which is the derivative of the derivative, it's a product rule. First times derivative second, plus the second times derivative first. So first times the derivative of second. So derivative of cosine 3 theta is negative sine 3 theta. And then by the chain root times the derivative of 3 theta. Plus second function times the derivative of first. So derivative of negative 3 sine something is negative 3 cosine of that something. Negative 3 cosine of sine 3 theta. And by the chain rule, it's times the derivative of the inside. So now the derivative of sine 3 theta is, again, we just did it, cosine of 3 theta times 3. And yes, you could clean that up, but I don't think it's worth it. Okay, we'll just leave it like that in the interest of time. Okay, 61. I have to copy down all this stuff here. So capital F of x is f of g of x. And he gives you all this stuff. F of negative 2 is 8. F prime of negative 2 is 4. F prime of 5 is 3. G of 5 is 2. G prime of 5 is 6. Okay, so the first thing I'll do is see if I got it all. F of negative 2 is 8. F of negative, F prime of negative 2 is 4. F prime of 5 is 3. G of 5 is negative 2, sorry. Negative 2. And G prime of 5 is 6. Okay, find F prime of 5. All right, so I'm going to do F prime of x is little f prime of g of x times g prime of x by the chain rule. Capital F prime of x, this is just from the definition. Little f prime of g of x, g prime of x. Now I plug in 5 everywhere. Put a 5 here, 5 here, 5 here. So capital F prime of 5 equals f prime of g of 5 times g prime of 5. Okay, then I just plug in stuff. So g of 5, where is g of 5? Negative 2, right? So this is negative 2. So I want f prime of negative 2, g prime of 5. Okay, then I just pick everything out. F prime of negative 2 is 4. And g prime of 5, where did it go? 6. So it looks like the answer is 24. Okay. And let me see if I have time for any more. 3.5, 15. I can't do that quickly, but I think Prasanna tried to address that. But if that didn't help, I can do it again. And 31, I can't do that quickly either, unfortunately. Okay. So if you want to ask it again tomorrow, that'll be okay. All right, so I have to stop the share here again. And let's see. Okay, so Prasanna tried to address that. If that's not good enough, you can ask again tomorrow. Have maybe 4 minutes left. So I don't have time for these problems, unfortunately, but I'll let you ask again tomorrow. Maybe it's a good time to stop, because if I do any problem right now, it'll take us past 1 o'clock. Okay, thanks, Prasanna, for trying to do that. But if somebody wants to ask again, that's perfectly fine. All right, so tomorrow is Thursday, as usual, on this sheet. The day before, you can take the whole period for questions and answers. But when that stops, I'll start doing some more stuff. But we'll see how it goes. But I'll let you ask questions tomorrow, and then I'll go on with new stuff. All right, so that'll be it, folks. I'll see you all tomorrow. Okay. All right. Have a good day. See you. Bye.
Bye, Professor.
All right. Have a good day.